I would ask Mr. Said Musa to come out and present us his paper named Fracture Behavior of Roll-Bounded Aluminum Bars, Aluminum Multilayer Composites, Concept of the Maximum Undamaged Defect Size, DMAX. So here you go.
Thank you. Hello everyone, my name is Dr. Said Musa. Today I'm going to present about a work that we have been done in our group. My friend Amr, he was supposed to be here, but due to some travel circumstances he couldn't make it. I have done all the experimental work. He has done some of the most of the numerical analysis. Since I'm the last one before the lunch break, I'll try to make my presentation light and healthy. So my presentation will be about the fracture behavior of roll-bonded aluminum brass aluminum multilayer composite by using the concept of the maximum undamaged defect size. My outline presentation will be about the motivation behind this work, the main objective of this work, some of the material that we have been using, the experimental and simulation. Since we have some using a new concept, which is the maximum undamaged defect size, we would like to explain some about the surface preparation and experimental setup. Finally, we'll have some experimental and numerical result, and finally, some conclusion that had been drawn from this study. As we all know, like multilayer composite or bilayer composite is well known since down the history. It has been used in many of different military applications to use for manufacturing some kind of the warrior shield. However, nowadays it has many different kind of applications, starting from cladding system, when we have like a material that an expensive material, clad expensive material for corrosion resistance, for fracture behavior, for toughness. Also it can be used for bilayer for material actuator, also for metal and polymer. We can use it for some sound and vibration noise control. Also, composite or multi-layer composite can be designed to improve some of the mechanical properties like fracture toughness, ductility, formability, and wear resistance. For motivation for using the process, well, we have used the roll bonding. It is a non-complex process compared to many different kind of processing for manufacturing the multi-layer composite. It is scalable. It helps to provide better dispersion of reinforcement particle. If we use some kind of reinforcement, we use it for many of our previous study. So we use the roll bonding to manufacture the aluminum brass aluminum sandwich composite. So the main objective for this work is to manufacture aluminum brass aluminum by using warm roll bonding. When we incorporated some of the preheat temperature, so we can reduce the work that needed to be to produce a robust bonding between the aluminum and brass. Also, we investigated and understand the effect of the process parameters such as surface roughness, preheat temperature, rolling speed, and thickness reduction. And finally, we analyzed the effect of the non-damaged zone after the sanding on a direct adhesion strength. Since we have some sanding, we get some imperfection material, so we try to study the effect of this one in the adhesion strength experimentally and numerically. So, for the material that we have used, here's some of the specification of the aluminum and brass for the Young modulus and some of the chemical combustion for both materials, just only for reference, and that we use for the numerical analysis. Okay, for the warm roll bonding procedure, in order to have a very good bond for the material when we cut it to a different size, we did some kind of surface preparation by taking out some of the contamination and put it in ethanol pathway. Then we sand it and preheat it for a certain temperature, as what we can see here. Then we inserted the brass in between the two aluminum skin. Then we rolled it right away after the preheating temperature. I'm here just showing the process parameter that we use for the and their settings for the process. We use the surface roughness with different grit size, so we have different surface roughnesses. Preheat temperature, we have tested many different preheat temperature, but for the current study, we are just showing that the preheat temperature that has been used in this study. The rolling speed, we have used like the 45 rolling speed, and we use different thickness reduction because we need some of those data for the numerical analysis. In order to investigate the surface roughness or the effect of the surface roughness or the effect of the undamaged defect size suit, we use different sandpaper with different grit. This is the adhesive aluminum. This is the grit 80, 50, and 36. For this current study, we did the sanding in this way and we did it in the other way so we can have some undamaged defect size, and we measured the surface roughness for most of the material. We used the 80 and 50 for this study. As we all know, like we use the TPL test in order to investigate the adhesion strength between the two. The multi-layer composite between the moving fixed grip and moving grip, and we did measure the resistance. We have the load, the maximum load, and we divide it by the bond width to have the average beam strength for all the samples. Here's just showing one of the experimental. We have done it for most of them, but since most of this work is about the numerical, I'm just showing here some of the experimental result for this load versus displacement for the this sandwich composite at this condition. For the rolling speed 45, 60 reduction, 200 preheat temperature. We reach the maximum load when the crack is initiated. We start to have some like a drop. Then we take the average load, we divide it by the bond width of the sample, which is about I believe 20 millimeter. For the numerical analysis, here's the condition that has been used by our group. For the numerical, the length was like fixed, the different width, different aluminum thickness. The brass was like they fixed it at 0.2, and for the imperfection, we used different starting from 0.5 up to 6, and we studied the effect on the beam strength. So, for the numerical study, it was divided into two phases. The first one, we studied the effect of the contact area at the interface. Then we changed the thickness of the aluminum since we have two skin aluminum. Then finally we study the effect of the presence of the imperfection at the aluminum brass interface in the peeling behavior. Just here showing just some of the peeling simulation that has been used, or using the basic fracture mechanics. We used I believe they used the VCCT and node surface theory for such kind of the simulation. So for the result, comparing between the numerical and the experimental result, we can see how for the first stage until the max point, we have a linear agreement until we get the maximum. Then the crack is initiated. We have a very big drop, or we can see sawtooth that can be phenomenon for this this kind of the composite. Until this stage, we can for the maximum load, we have a very good agreement that we can use for such kind of the study. Here we just showing some of the effects. As I said before, we studied the effect of the aluminum plate width, then we studied the effect of the thickness, then we studied the effect of the imperfection. So for the effect of the aluminum plate thickness, as we can see, we have different aluminum thickness, and as the thickness is increased, we have an increasement in the maximum load for all the samples. So here we normalize it so we can see how we can predict the effect of the peeling strength with the reference, and we can see we have no effect until we get the ratio of the two. Then as the surface roughness, as the thickness, the sandwich. As the aluminum thickness increase, we have some effect in the peeling strength. Here we show just only the UZ, which is the displacement when the crash is initiated, which is at the maximum load. From the stiffness point of view, the stiffness increased by increasing the value of the TAL, and subsequently the displacement at the commencement of the peeling is decreased. Here we show finally and secondly the effect of the width in the contact area. As we can see as before, most as the width is increased, we have an increasement in most of the curve for the peeling load and the average peeling load, and we can see the effect of the width. It's a very good parameter, so we can predict the peeling strength, how it's affected with the linear way for all the width samples. Finally, the effect of the temperature the imperfection hole in the peeling load. We used starting from 0, there is no hole, and we started to increase the effect of the size of the D. All of them, we can see, they have almost the same peeling load. However, as this increase, we have an increasement of the average peel strength. When we normalize it, we have up to the ratio of the 20%. Before that, like we have a decreasement in the peeling stress. So for this, based in the present analysis, we can see it can be concluded that the ratio of the maximum size of undamaged defect Dmax to the interface width is around equal to 20% for just current study. Just showing here some of the effect of the imperfection with the zero. We can see like there is no stress concentration. As the hole diameter increases, we saw like for the von Mises that we have an increasement around the hole, we get some kind of stress concentration. Yeah. For like the effect of the imperfection, we have done some of the experimental. This is the first one that I show for the experimental work. So we did have some experimental, like we used a sample with a rough surface roughness, which produce a surface with high asperity and deep values, and we can see like that increasement. We have a very good like increasement with like around 30% increase for the average build strength, and we're still working to test like different reduction, testing different temperatures, so we can generalize the concept of the Dmax or the undamaged defect size zone. Here's some kind of the conclusion that we can see the experimental results that the mechanical interlocking was the primary adhesion mechanism. Also, there is no effect on the aluminum thickness as I mentioned before in the bending strength. Up to like the ratio is equal to 2, while by this point the build strength is increased by increasing the T aluminum. Finally, the ratio of the maximum size of the undamaged defect size to the interface, which is equal to 0.2. This value is just only valid for a circular imperfection and surface roughness of 3.75, which is the grade 80 that we used as in the beginning of the aluminum brass interface. Finally, the model was verified, and we try to do more investigation so we can generalize it for different kind of material. I would like to acknowledge the agency for funding such kind of research. Also, my friend back home in USA, for Dr. Gab Kim and Dr. Mina Bastaros for their discussion, and thank you.
Thank you, Mr. Said. It was quite interesting, and right now we can go to the discussion session. So my idea would be to start with if somebody has any questions for Mr. Said, since he's already here. And yeah.
Oh, thank you. I was just wondering how it is you get mechanical interlocking in this process.
Yeah, like for the experimental work, we have done this one with the different aluminum, different like metals and different metal and aluminum. Different materials like metals and metal and polymer. For the mechanical interlocking, we for the experimental we create different structure at the interface by using sanding or by using knurling. When we do the fracture, I have to suppose like to show some of the fracture. Some of the fracture surfaces. We can see there is a cohesive failure at the interface between the aluminum and the brass. We can see like there is some kind of the mechanical interlocking. Some of the brass material, aluminum material interlocked with the aluminum at the interface, with the two interfaces.
So you think you get mechanical interlocking because it merely penetrates
into at the intermetallic interface.
Okay, that's quite surprising. What was the temperature of that process?
It's around like preheat, it's around 200 C.
Okay.
We didn't get to the recrystallization.
Relatively low. Okay. Okay, I've got other questions, but for other authors, sorry.
Yeah, okay.
If you want to finish with this.
Is there any other questions? Okay. No, so thank you very much for the information.